I have a question regarding the exam.
Okay.
What are we allowed to bring into the exam?
So if you have the equations handbook and a calculator and something to write with.
Okay, thank you.
Okay. I'll sort of say that uh, everyone, I hope, will have some sort of paper or something. So the way we'll do this is I will send out a PDF of the exam. And then what I would like to ask everyone to do is just write their answers labeled with the problem number and their solution, and then just send take a picture of each one of the solutions and then send it or upload it. Um, I'll tell you more about it as the time approaches. But that'll be the process because that's the only way we can sort of do this at this point under the current situation. So does that make sense? So what I'll do is I'll make a PDF accessible to everyone with all the questions, and you can. I hope everyone has paper at home or something that they can put their solutions on, and then just send up the pictures or photographs of your solutions, and just label each solution according to the problem number. Does that make sense? Okay, that's pretty straightforward, I think. And so the equations handbook, if you have it, and I hope everyone does, because you will need it next semester for Chem 444, because we will have equations in that book for exams. Something to write with and a calculator. Okay, any other questions? And I say that if you've done the homeworks, I have extended the homework for the entropy problems, just because that wasn't due today, so I made an extension for that. And if I think the reading has been pretty clear on some of the more details of calculations. I've gone through a lot of concepts in the course. And if you understand the concepts, you should really have no problem with the exam. Okay, so let me continue if there are no other questions on the technical material in the course. So today I want to finish up with a couple of examples for adiabatic processes and isothermal processes. And before we do that, I want to address the constant the heat capacities that we've been introduced to for an ideal gas. Okay, so any questions on the Joule-Thomson experiment? The Joule-Thomson experiment really was about the points I made last lecture, and I will upload that lecture. So today we'll continue and we'll see something relating to total differentials again. Again, it's just more practice for that. So heat capacities for ideal gas, something that can be modeled by an ideal gas equation of state. And we know that the ideal gas equation of state is this, okay? And we have seen that Cp of T in general, right, is the partial of H, which we can choose to write this way. Okay, so the constant pressure heat capacity is this partial derivative of the enthalpy with respect to temperature at constant pressure. And N is constant for our purposes. And we saw that Cv, the constant volume heat capacity, is again the same thing. It's a partial derivative with respect to temperature, but in this case of U, the energy of the system with respect to temperature at constant volume. Okay? And these are the most general. So these expressions are general. They apply to any. They apply to any material. Okay, in this form. because we haven't made any stipulation, that's it. They're just sort of a statement mathematically of what these entities are, Cp and C sub v. So let's see what we get when we do this for an ideal gas. Okay, so what we want to do, and in fact, what we can do is say that, so these are non-molar properties. So H and U, as we've written them here, are extensive. Okay, so if I double the amount of system, then I'll have twice as much H and U. Okay, but we can always make these guys intensive by dividing through by the number of moles. So for instance, we define the enthalpy as H is equal to U plus PV. Okay, and this is V here, the volume. This is extensive, H and U. So both of our thermodynamic functions here, H and U, are extensive. Okay, but we can make this whole thing intensive by dividing by N, which is the moles. Okay, and so if we divide H by N, that's defined as U divided by N plus, well, we already know pressure is intensive. We can't divide pressure by N. So what we have to do is divide volume by N, okay? But then this just becomes the molar enthalpy, H bar, and your textbook uses an H sub M, okay, for the molar property. We can use H bar, it's the same thing. Okay, so H molar in your text is equal to H bar, and so this is just the molar enthalpy. Okay, and that's per mole. So getting back to this expression, we see then that this is just going to be H bar is equal to U bar plus P times V bar. Okay, so now we've made this intensive. So everything there is an intensive variable or an intensive function. It doesn't depend on N explicitly because we divided by N. Okay? So if we go back to our expressions here, for the general Cp and Cv, we can make them intensive now. We can make these heat capacities intensive per mole. So we can write Cp of T, which is equal to partial of H with respect to temperature at constant pressure. We can divide both sides by N. So if we divide by N, number of moles, we get here Cp bar, which is the intensive or per mole. And then this side, we have dH bar, dt at constant P. And of course, well, we don't have to have N anymore because now it's intensive. So it doesn't matter. Okay, so we can just write this as P. Okay, and we can write the same thing for Cv in molar form, which is the partial of U, which is molar now with respect to T at constant V. But of course, this has to be V bar now. Okay, and so all we did here was divide by N to get these intensive properties. Any questions? Okay, great. So let's see the relationship between Cp and Cv for an ideal gas, because this is important and we'll use this result. Okay, so again, this is something that's an ideal gas equation of state. And we're going to start with our definition of Cp, and we'll just use an equal sign. So that's just dH bar dt at constant P. Okay, but we know what H bar is. That's just U bar plus P V bar. So C bar of T is going to be the partial derivative with respect to temperature of this whole thing, U bar plus P V bar. Okay. And what we're going to do is hold the pressure constant. Okay, so what I did was substitute H bar into here. Okay, and H bar is the sum of U bar plus P times V bar. And we take the partial derivative with that sum at constant pressure. And since we have a sum, we can take the derivative of a sum as the sum of derivatives, and that looks like this. The partial of U bar with respect to T at constant P. And since pressure is constant, the derivative of this product PV bar, we can hold P constant. So we can treat that as a constant. So that P comes out. And this is just going to be d dt at constant P. Okay, so did everyone see that? Is everyone clear on what that manipulation that I just did? If not, please ask. Okay. And so we see here that putting all of these types of constraints, so because P is constant, I could pull out the P here. I didn't have to worry about its derivative. It's just a constant. And that's because we are dealing with the constant pressure heat capacity. So let's continue. Okay. How are we going to treat this term first? Okay, and let's take a look at that. Well, I have to take the partial derivative of U bar with respect to T. One can do that, okay, if one knew what the total differential of U bar is. Okay, and so this is the importance of these total differentials. Because once you have a total differential, right, which is a total change of a function with regard to its dependent variables, you can in fact manipulate that total differential to get other rates of change. And I'll show you how, and it's a very cool trick, and it's a very powerful trick. So remember we saw that du, remember when we wrote this as a function of t, and now we can write this as v bar, was cv bar of t times dt plus the partial of u bar with respect to v bar times dv bar at constant t. Oh, and this should be at constant v bar. Okay, so this I wrote, let me write this in terms of the external form just to remind you, because maybe it's a little bit more explicit. Remember we wrote this, cv of t. I don't need this here. Okay, cv dt plus the partial of u with respect to v at constant t and n times dv. Okay, where n we said was constant. So remember this term, this equation. Again, these are very general. These are the general forms. So I think everyone remember this one. Okay, we can use these guys, and by dividing through by n, we can get the intensive form in terms of the molar properties. Okay, is everyone clear? Did I leave anyone? Okay. So we can make use of this expression now to get any other partial derivative of u bar in terms of any other variable. That's one of the powers of total differentials. So let's use this. Let's start with this guy. Okay. What I need here is the partial of u bar with respect to t at constant pressure. At constant pressure. Okay. In this total differential, I don't have pressure at all because the way we set up this dependence of u on independent variables was as t and v, or t and v bar. But I need to have a partial derivative of u with respect to temperature at constant pressure. Somehow we need to think about pressure in this. So the cool thing you can do now is to start with this expression, okay, and say, all right, well, I'm going to take the partial of u. Okay, it's still a function of v r with respect to temperature. at constant pressure, okay? That's what I want, but I'm going to start with this expression. And then I'm going to say, all right, well, I have this first term I have to deal with. Okay. Now CV bar is just it's a parameter that's going to depend on temperature, but it's temperature dependence. Okay, we can treat it as a constant for the moment. Okay, we'll treat it as a constant for a moment. So that's going to be CV bar of t, okay, times the partial of t with respect to t at constant p. Okay, so that the term in the red box, what I've done there, does everyone see what I did there? So I let CV be a constant. Okay, and then I said, all right, well, I still have to take the derivative of whatever is in that product. So that's the rate of change of t with respect to t, but it's at constant pressure. Is everyone clear? Okay, great. Now we do the same thing with the second term. Okay, so now we have the second term here. Okay. So in these total differentials, whatever comes before that term the term like dt or dv bar, we can always treat as a constant because it's a rate of change under a certain condition. So for instance, the partial of u bar with respect to v bar right here at constant temperature, this is a rate of change of u bar as V bar changes, and again, these bars are molar properties, okay? So it's a change of the molar U with respect to molar V under a very specific condition, and that is at constant temperature. So for a system, if you hold temperature constant, how does U bar change when you change V bar? This is sort of like, you could think of this as a rate of change at a very specific set of conditions, and it doesn't ever change. So the partial of U bar with respect to V bar at constant T, you can treat it as a constant. Okay? You can always treat that as a constant because it's just a rate of change under a given set of conditions. Does that make sense? Okay? I hope. Or is that a bit confusing? Okay, I don't hear anything. Okay, so I'm going to continue. Okay, I really want people to be clear on this. Okay, so what we're going to do then is write for this term, partial of U bar with respect to V bar at constant T, which we said is a constant. And then here what we'll say is partial of V bar with respect to T at constant P. So this is the term that has that partial with respect to temperature at constant P. Because remember, we let this guy be a constant rate of change under a different set of conditions. Okay. So the only thing that we have to worry about with respect, taking a derivative with respect to temperature at constant pressure then is that V bar term. And that's this guy right here. Okay, everyone clear with that? So that allows us to get this term, that partial of U bar with respect to T at constant pressure, which is this term in our CP bar of T. Okay, now we just kind of go in and fill things in. Everyone clear? Okay. For at least this guy. Let's finish this up and continue and fill everything in. So this guy is just CV bar of T. What's the partial of T with respect to T at constant pressure? Can anyone tell me a number for that value? If I were to hold pressure constant and if temperature changes, what's the rate of change of temperature with respect to any change in temperature? So for instance, if temperature changes by 1 degree Kelvin, then what would dT have to be? What is the rate of?
It'd be 1.
Yeah, it's 1, right? Because if temperature changes by 1 Kelvin, then both numerator and denominator are 1. Something changes by itself. It depends on itself. It has to be 1. So that's awesome because we don't have to worry about this thing. It's just 1. Okay, so here we just have 1. That's cool. All right. Now let's go to the second term. For an ideal gas, what's the second term going to be? Does anyone remember? Well, what's du bar dv bar at constant T for an ideal gas?
22.
Sorry?
Is it 22 liters?
No, okay, so how does U bar change with respect to volume? No, it's, okay, so it is a number, but it's not 22. So what is how would you, so remember when we were talking about the joule-free expansion. So the joule-free expansion, this is the partial derivative that we obtained. And there was a special thing about an ideal gas when it comes to this partial derivative. Partial of U bar with respect to V bar. Does anyone remember? Okay, so it turns out that U, recall, U bar or U, same thing for an ideal gas, is only a function of temperature. It doesn't depend on any other variable for an ideal gas. And so what then would be the partial of U bar with respect to V bar for an ideal gas, since we're doing everything here for an ideal gas?
Zero.
0. That's exactly right, because it doesn't depend on volume. So partial of U with respect to any change in volume, there's going to be no change in U if volume changes, because U does not depend on volume. So we don't have to worry about this. So at this point, we can just leave this guy here. Okay. So the partial of U then, or U bar, with respect to T at constant pressure, is just equal to CV bar of T. And since that's multiplied by 1 here, we don't have to worry about it. So this is what we get for an ideal gas. Okay, did everyone see that? Okay, that's great, because now what we can do is put that result here, okay, because this is what we were after, right? The relationship between Cp and Cv for an ideal gas. That was our whole point to start with. So we have this guy now, the first term. Okay, we know what partial of U bar with respect to T at constant P is. That's just Cv bar. So let's go back. Cp bar of T is equal to Cv bar of T for an ideal gas. Now we just have this term left. Right here. We have to worry about this term. Okay. Plus P times the partial of V bar with respect to T at constant P. Again, this is for an ideal gas. We're only interested in an ideal gas for the moment. Okay. Well, what's V bar for an ideal gas? Because we have to evaluate this partial derivative. Well, we know that P times V equals nRT. Okay. We can write this. Divide both sides by n, and then divide both sides by P. You get RT over P, but that's just V bar is equal to RT over P, because this guy is V bar, V divided by N. Okay, so we know that V bar is RT over P. For this term, we need to take the partial derivative of V bar with respect to T at constant pressure, but that's pretty easy. That's just equal to the partial of T okay, and where now I've substituted RT over P for V bar, and I made sure that I carry this notion that P is constant. Okay. But what's the derivative of RT over P with respect to temperature at constant pressure? R over P, right? That's the only thing, it's just a very simple derivative. So this is just going to be R over P. So partial of V bar with respect to T at constant pressure is equal to R over P. We can substitute that result here. Okay. We can substitute it in. So it's P times R over P, because P times the partial derivative of V bar with respect to T at constant pressure is just R over P. So this term is going to give us R. Okay. So what we're left with then is Cp is equal to Cv. Oh, these are molar, I believe. Yep. Plus R. And in fact, for an ideal gas, it turns out that Cp is only a function, it's a constant for an ideal gas. It doesn't depend on temperature, as does Cv. So these two are constant for ideal gas, something that's modeled by the ideal gas equation of state. So in the case of an ideal gas, Cp bar is equal to Cv bar plus R. And that's the result that we obtained. And this result was obtained by using this idea of du is equal to Cvt dt plus the partial of u with respect to volume at constant T and N times dV. Okay, so this is the intermediate step that we had to use to arrive at this. Okay, so this is an important result. Okay. So any questions as to how we arrived at that? So the big point here is that we manipulated this total differential. Again, we needed to obtain a total differential of u so that we could use it for something else. And so this intermediate step was critical. Okay, and so I would encourage everyone to go back to these notes, in your notes, and understand how we arrived and used this total differential. If there are any questions, and if there are any questions, you can ask now. We can. No? Okay. So we're going to use this result. Okay, so let's continue on then. I'm going to take a look at a process right now. Again, now we're going to focus on an ideal gas. Okay, so let's consider an example. this is the reversible. Okay. Adiabatic. Expansion or compression. It doesn't matter. We're going to have a volume change. Expansion, compression of an ideal gas. Okay, so by this, what I mean is that volume will change. Okay, so there will be a V1 and a V2 in this process. So we're going to consider a process. Okay, it's reversible, so there's a lot of information already. It's reversible, it's adiabatic, and the volume will change, and we have an ideal gas. So just in all of this, there's so much information that you can consider a solution or a problem that may ask you for some implications of this process. The way we'll start is apply the first law. Okay, we haven't done anything else but the first law, so we can apply the first law. And in the most general form, in its differential form, we know that du is equal to dq plus dw. Okay, so here's an example of applying the first law now, using everything that we've learned. But since it's adiabatic, what can we say about one of the terms in our expression of the first law?
dq is 0.
Yeah, exactly. dq is 0 because the process is adiabatic. And by definition, an adiabatic process, in the idealized case, of course, has no heat interaction with the environment. So in this case, du is equal to dw. Okay. All right, that's great. If it's reversible, because that was given in the problem statement, if it's reversible, then we can say something about dw. We know that dw reversible then. Well, let's start with the general form. You know, dw is just minus p external times dv. But we were told that it's reversible. So dw reversible is minus p times temperature, volume, n times dv. We can make that substitution because process is reversible. Okay, that's given in the problem statement. Okay. Any questions so far? Okay. We're also told that the gas is ideal. Okay, so the gas is ideal. It's modeled by the ideal gas equation of state. So pressure of temperature, volume, n is equal to nRT over V for ideal gas equation of state. So dW reversible is equal to minus nRT dV over V. Okay, so that's an intermediate thing that we keep in mind. Any questions? Okay, so we keep that in. Now let's take a look at the du term. Okay, and so again, this is ideal gas. It's kind of that. Du of an ideal gas, we saw that U for an ideal gas is only a function of temperature. U is only a function of temperature for an ideal gas, and that's just CV, ideal gas, times dT. And CV for an ideal gas is independent of temperature. Okay. And what we can do is write, all right, well, we can modify this. This is extensive, okay? And instead of using an extensive CV, we can write du ideal gas is equal to N times CV bar. Okay, so here's a little bit of practice in converting molar properties into non-molar properties. Since CV bar this guy is molar. If we multiply it by n, we'll get the total CV. That is extensive, which is given by this guy. Okay, so we can write du ideal gas is equal to n times the specific or partial molar constant volume heat capacity times dt. And we can write this expression because, again, U is only a function of temperature for an ideal gas. Okay, and this came about from our discussion of the Joule-free expansion. Okay, if you recall, or if you might have already read this in the text. Okay, the stipulation I'm going to make now is we'll just take n to be 1. It doesn't really matter, so take n is equal to 1 mole. So what we have here then is du ideal gas is equal to CV bar for an ideal gas times dt. Okay, and that's because we're going to just say that, okay, we have 1 mole and is equal to 1. So now we have this, right? So we can put these two together now for our process. So again, the process is a reversible adiabatic change in volume of a system that's modeled by the ideal gas equation of state. Okay, and that's really what this was right here. Reversible adiabatic expansion compression, volume change for an ideal gas. So now if we put these two expressions together, this one and this one, what we have here is CV bar ideal gas times dt is equal to minus nRT dV over V. Okay. Everyone okay with that? All right, awesome. So now we're just going to do something called separation of variables. Okay, let's see. So once we have this is in differential form. I have differentials around these dTs and dVs. Okay. If I want to know how volume and temperature change now as a function, as a result of this process, what I can do is integrate this equation. Okay. And I can do this very simply because you can manipulate this equation to separate the variables so that on one side I have variables that are only temperature dependent, and on the other side I only have variables that are volume dependent. Okay? So the only problem really is this guy, this temperature on this side, but it's not that much of a problem. Okay? On the right hand side I have this mix of temperature and volume, and I know that temperature and volume will both change in this process. Okay? I know that a priori, and that's something I want to show you and make a point about it using this example. So what I'm going to do is bring the temperature from this side to that side, and that's going to look like this. What that means is I just divide by temperature on both sides, and then here I'll just have minus nR dV over V. And what happens now is that I have variables of temperature on one side and volume on the other. Everything else is a constant. So I don't have to worry about anything else. And oh yeah, let me just say that n is 1. We said that n is equal to 1. So in this case, we're just going to let n equal 1 mole. So this expression even further reduces to CV bar ideal gas dt over T is equal to minus R dV over V. Okay, so this is another intermediate result. Any questions? Where CV bar ideal gas and R are constant. And CV ideal gas is constant because it's an ideal gas. I haven't proven this to you at the moment. It's just something you'll have to accept for the moment. But you can actually prove that. And later on, you will be able to once we have more machinery from thermodynamics. So this is our intermediate result. And now we just integrate. So this is a very simple integration. Okay. CV is a constant, so we don't have to worry about that. We have an integral of dt over t from T1 to T2, because we know that temperature will change, and that's going to equal minus R is a constant, times the integral from V1 to V2. Remember, volume changes in this process of dV over V. Okay. So I can do the integral, dt over t, dx over x, 1 over x dx, all the same way, right? That you've seen this before. This is just going to equal, does anyone remember what the integral of 1 over x is in its most general form?
ln.
ln, that's right. So this is just going to be an ln term. And of course, I'm going to have ln of x final and ln of x initial. But when we take the difference of two logs, it's just a ratio of the logs. So this is just going to be a log T2 over T1. Okay. And just to refresh your memory, this would be, if you did the integral, natural log T2 minus natural log T1. Okay, that's what that is. And so we can write this as a ratio in a log. Refrain and be very careful of writing this as natural log T2 minus T1. No. Okay. Refrain yourself from writing that, because that is not what that integral is. It's the natural log of T2 minus the natural log of T1, not the natural log of the difference, which is T2 minus T1. Okay, so be very, very careful. Be careful of that. Okay. So then here we can do the same thing with the volume integral. We have minus R natural log V2 over V1. Okay. Now we'll just sort of clean this up a little bit. We'll bring this down here. Okay. So natural log of T2 over T1 is equal to minus R over CV bar for an ideal gas times the natural log of V2 over V1. And that's just rearranging the equation at the top of your screen, okay, by bringing over the CV bar for an ideal gas to the right-hand side. And so R over CV bar is just a constant. Okay, any questions on that? Okay, so what we can do now is write this expression in this form is equal to natural log V2 over V1. And here we write minus R divided by CV bar, ideal gas. Okay, we can do this manipulation with logs. So since I was multiplying log of V2 over V1 by this constant, right, I can raise that ratio and take the log of that ratio raised to this constant. Okay. So this is something you've seen before. If you don't remember it, it's a property of natural logarithms. So I can do that. So a times the natural log of x is equal to natural log of x to the a, where a is a constant, some constant. Okay, this is just a property of natural logs. It's not something that, you just know it. It's just something. And that's why I can write this expression in this way. Okay. So let's see what R over CV is. Remember, we said that Cp for an ideal gas is equal to CV bar of an ideal gas plus R. We just proved that a while ago. Okay. So if I divide through, let's see, how do we want to do this? Let's divide through by CV. So what we have here is R over CV ideal gas is equal to CP ideal gas over CV bar ideal gas. Right, so we're going to divide -1. Okay, so what I did here was I brought the CV bar over to this side, and then I divided everything through by CV bar. And that gives me this. Okay, and so minus R over CV ideal gas is just going to be 1 minus CP over CV.
Is this the gamma term?
Gamma term, exactly. That's exactly right. So we're going to define gamma. So we're going to define something so we don't have to keep writing this stuff down. Gamma, it's just a ratio. It's nothing profound. So nothing to get too worked up about. It's just that so we don't have to write this ratio all the time. So we're just going to define gamma as CP divided by, okay. So then this just becomes 1 minus gamma. Okay. And again, gamma is just this ratio. It in our derivation, we got this ratio, so we just let it be that, so we don't have to keep writing it. Okay, that's all it is. So we can then go back and simplify this expression. Natural log of T2 over T1 is equal to natural log of V2 over V1 raised to this minus R over CV ideal gas. Okay, but that minus R over CV ideal gas is this guy right here. And we saw that it's just equal to 1 minus gamma. So we have your natural log T2 over T1 is equal to natural log V2 over V1 to the 1 minus gamma. Everyone okay with that? It turns out that gamma is greater than 1 because CP is greater than CV. Okay? And this is in general. CP is greater than CV, so gamma is greater than 1. And here. So this is our final expression. Okay? I want to make one point here. Is everyone okay with everything? Gamma is nothing more than just this ratio. We can choose to, I could have chosen not to introduce gamma and just keep everything in terms of CP over CV. Okay? It just makes life easier when you don't have to write more things than you have to. So, you know, and you'll see a lot of this in quantum mechanics next semester when we have all of these parameters, people just lump them together so you don't have to keep writing them over and over and over and over. Okay? So that's what this gamma is. So I want to make one final point, okay? And that is this. We said that this is an adiabatic process. That was how we started out. And we all agreed then that for an adiabatic process, by definition, dq has to be 0. There is no heat interaction, okay? But our relationship, our final expression, the first law analysis of this process shows us that because there's a volume change, right? We said there's an expansion or a compression. There's an associated temperature change. So this expression explicitly and directly proves to you that even if a process is adiabatic, meaning that dq is 0, dt is not 0. Okay, so one cannot associate an adiabatic process with an isothermal process. And an isothermal process is one where temperature does not change. Okay, so this is direct and explicit proof that adiabatic does not mean temperature is constant. Adiabatic only means that Q and dQ are 0, but it does not mean dt or delta T is 0. And this expression shows you explicitly that that is the case for an adiabatic process. Okay. So what if you have an expansion? What if V2 is greater than V1? Last point. I know if if V2 is greater than V1, if you have an expansion, what can you say about the temperatures, knowing that gamma is greater than 1? So if V2 is greater than V1, this is our relationship. We know that gamma is greater than 1, so the exponent is going to be negative. Okay, so V2 over V1 is going to have an exponent that is negative. And when you have something that's raised to a negative, what does that mean?
You're gonna flip the argument.
Okay.
The ln.
Okay. So that's okay. That's fine. You can do that. Let me see. So let's just say if we have an expansion. So you're right, but I want to just go at this a different way. If V2 is greater than V1, you know that the argument is going to be greater than 1. Is that right?
Make the number smaller. So the ratio of T2 to T1 will be small.
Okay. That's exactly right. So since gamma is greater than 1, this exponent is going to be negative. V2 over V1, though V2 is greater than V1, V2 over V1 would be raised to a negative exponent, meaning that that's going to be a fraction. Essentially, it's going to be a fraction. Okay. So if V2 is greater than V1, V2 over V1 raised to the 1 minus gamma is a fraction. Okay. It's not going to be greater than 1. It's going to be something that's less than 1. Therefore, T2 over T1 is going to be less than 1. It's going to be a fraction, which means then that T2 is going to be less than T1. And what does that mean if T2 is less than T1? What happened in that process? We had an expansion in terms of volume, but in terms of temperature, we had, what did this?
Decrease?
Yes, and that means the system cooled. That's right. So again, we had an adiabatic process in which there was no heat interaction, yet the system cooled, the temperature changed. The other thing is the system expanded, V2 is greater than V1. That means the temperature had to drop. And this is something you've already been exposed to. When a system has an increase in its volume, the temperature has to drop. If you compress the system, the temperature will increase. And again, you can see that in this expression. If V2 were less than V1, then T2 would have to be greater than T1. Convince yourself of that. But again, all of this is encoded in this very compact equation for an adiabatic reversible process for an ideal gas. Okay. Again, one final time I'll say this: dq is equal to 0 for an adiabatic process, but that does not mean dt is 0 or delta t is 0. Very important. Okay, I went over, I'm sorry, but this is very important. Students often make this confusion every year, so I want to make sure that everyone gets it 100% right this year. Okay, any questions, comments? Okay, my apologies for going over. Thank you for your attention and participation, everyone, and I'll post the notes as well. Okay, have a great weekend. It's Friday. Have a great weekend. Take care.
Thank you. Have a good weekend.
Thank you.